Hello, and welcome to Our Earth, its climate, history, and processes. I'm David Schultz. In this lecture, we're going to talk about the hydrosphere. This is the sum of all the liquid water on the planet. And so, what comprises the hydrosphere? 90% of the liquid water on the Earth is saline. In other words, ocean water. Only 3% of the water on Earth is fresh water. Of this 3% fresh water on the planet, 68.7% are tied up in ice caps and glaciers. 30% is found in underground aquifers and in groundwater. If we look at how this surface water is partitioned, 87% is found in lakes. 11% is found in swamps, and 2% is found in rivers. So, looking at how water is distributed on the planet, it's clear that the oceans contain the bulk of the water, but this is salty, saline water. We look at the distribution of land and oceans in the northern and southern hemispheres, we see that there's almost 5 times the amount of land in the northern hemisphere compared to the southern hemisphere. So in the northern hemisphere, we tend to think of the important influence that the land has on the climate, and we'll see that later in the course. Whereas in the southern hemisphere, the oceans really dominate the climate of the southern hemisphere. These ocean waters contain dissolved salts that we call salinity. We want to look at where this salinity comes from and what its composition is. The salinity comes from the chemical weathering of rocks on land, the salts that are brought up from the interior of the Earth in volcanoes and other hydrothermal vents. Of the salts that are dissolved in the ocean waters, over 85% of them are comprised of 2 ions, sodium and chloride. Sulfate, magnesium, calcium, potassium make up a lot of the remainder of the salts, the ions within the salinity, the dissolved salt content in the oceans. So where did the oceans come from? Where did the water come from? And how did they obtain the salts dissolved within them? These are the questions that we want to ask. We also want to look at how the volume and salinity of the oceans have changed over geologic time. There are 2 hypotheses for the origin of water on Earth. One postulates that the water derives from a terrestrial source, in other words, the interior of the Earth. The other postulates that the water comes from an extraterrestrial source. The extraterrestrial source hypothesizes that the water comes from icy comets or water-rich meteorites that impacted the Earth relatively early in its history. Although this is certainly a plausible hypothesis because comets are largely composed of ice and there would have been many more of them around during the early solar system, the ice in comets contains twice as much deuterium than is measured in present-day ocean water. Also, meteorites contain almost 10 times more xenon than is measured in the atmosphere. Thus, any hypothesis advocating for the extraterrestrial source of the majority of water on Earth would have to address these discrepancies with the modern Earth observations. Although it's a provocative hypothesis that the water on Earth, which is so essential to life, came from outside of the Earth, there's little evidence that suggests that the majority of water on Earth came from outside the Earth. Thus, the most reasonable hypothesis is that most of the water on Earth came from outgassing from the interior, and a small fraction maybe came from comets or water-rich meteorites also. Regardless of the source of the water, we know that the oceans formed on Earth by about 3.8 billion years ago. The composition of banded iron formations that are formed from the precipitation of iron from seawater in the Archean indicates that the rocks preserved their ocean water-like compositions during this time. So we know then that water must have existed on the planet as early as 3.8 billion years ago. The Earth continues to outgas water vapor to this day. For example, gases emitted from volcanoes along subduction zones can emit as much as 97% of their gases as water vapor. The water that is subducted within the sediments along with the downgoing slab puts water back into the mantle and then gets recycled through the outgassing back into the atmosphere. Much of what you see in a volcanic cloud is mostly liquid water and ice. Research aircraft flights through the Mount St. Helens volcanic ash cloud were described by one of the scientists on board as volcanic hail. By comparison, the Hawaii volcanoes, which occur along the mid-ocean hotspot, emits only 37% water vapor. Once emitted, the water vapor that was outgassed during the early evolution of the Earth condensed to form the oceans, with some of the water vapor remaining in the atmosphere. The primitive ocean would have contained very little salinity, but would have had some dissolved gases, such as bicarbonate from the dissolved carbon dioxide. Other emissions from these volcanoes would have formed the primitive atmosphere.